In this video, we are going to explain components of DC and RC circuits and clear up some common misconceptions. When we present a new example, we suggest you pause the video and predict what the results will be. After a few seconds, we will explain the outcome and the reasoning behind it. Just for reference, the current flow in the simulation we use is the electron flow, not the conventional current that you are used to seeing in class. You can see the difference in this image.
In this example, you can see that we have two batteries in opposite orientations. Do you think the light bulb is going to light? When the circuit is complete, the light bulb will not light because the electron flow from each battery cancels out. When the voltages of the two batteries differ though, the battery of greater voltage overcomes the other and there is current flow, and the light bulb will light.
In this next example, we introduce a new element called a capacitor. A capacitor, according to dictionary.com, is a device for accumulating and holding a charge of electricity consisting of two equally charged conducting surfaces having opposite signs and separated by a dielectric. For the following situation, we replaced one of the batteries from the first case with a capacitor. What do you think will happen when we close the switch? Initially, after we close the switch, the light bulb is fully lit because the current flows unhindered. At this point, the capacitor acts as a piece of uncharged wire. After time, once the capacitor is fully charged, no current flows and the light bulb does not light. In this case, the charged capacitor acts as an opposite battery. As I close the switch, you can watch the light bulb dim and current flow stop.
In this example, we have a capacitor in parallel with a light bulb, while in the previous example, the two were in series. What will be different between this situation and the last? Initially, the current flows equally through both branches and the light bulb is lit. After time, once the capacitor is charged, current only flows through the light bulb branch. As we open the switch, the capacitor discharges and as a result, it lights the light bulb.
In the following example, we introduce another element called a resistor. According to dictionary.com, a resistor is a device that introduces resistance, or the opposition to current flow, into a circuit. Here, you can see that we have a resistor and a light bulb in series. What do you think will happen? Initially, the current is the same throughout, but the voltage drops at the light bulb. The light bulb will remain the same brightness. The light bulb would be the same brightness if the resistor and the light bulb switch spots, because the total internal resistance of the circuit remains the same despite a voltage drop.
This situation shows a resistor in parallel with the light bulb. What do you think will happen? When the switch is closed, each branch of the circuit receives the same voltage, but interacts with it differently in terms of current. More current flows through the path of least resistance, in this case the resistor branch, despite uniform voltage, or the potential to have a current. In parallel, each branch receives the same voltage but a different current, while in series, the current is uniform throughout. The brightness in this situation remains constant.
Now we will start working with RC circuits. This circuit contains a light bulb, a resistor, and a capacitor in series. What do you think will happen? Initially, the light bulb would light up, yet not as brightly as it would without the resistor, because the resistor increases the total internal resistance of the circuit. Finally, once the capacitor fills, the bulb goes out as there is no current flow.
Pay close attention to the brightness of the bulbs when making predictions for this next scenario. Notice as the capacitor charges, the current in the circuit decreases and the brightness of the light bulbs decreases. Also, compared to the situation with only one bulb, these bulbs are dimmer because of the higher internal resistance. Use this advanced example to test your understanding of what we've learned so far. Make predictions about bulb brightness, current flow, and voltage drop. Because the branches are in parallel, each branch receives the same voltage. In the top two branches, the resistances are equal, and despite the different capacitor placements, the bulbs dim at the same rate as the capacitors fill. In the bottom branch, though, the four bulbs are all the same resistance, and because they lack a capacitor, they do not dim. The overall current drops as well as the capacitors fill.
In this next scenario, we have three resistors in parallel with three light bulbs. The light bulbs have the same resistance as the resistors. What do you think will happen to the current in each branch and the relative brightness of the light bulbs? As you can see, each branch receives the same voltage because they are in parallel. Since light bulbs act as resistors and each branch is of the same resistance, the relative currents of each branch are the same. The brightness will be uniform. While this example may seem complex, when you break it down, it's not that bad. This example is similar to the last, but in addition to the two parallel branches of equal resistance, we also have a capacitor in series. Considering what we have discussed about both capacitors and the idea of resistance, what is your prediction for this circuit? As in the last example, the two branches of equal resistance have the same current. However, over time, the overall current and brightness of the bulbs decreases as the capacitor charges. Once the capacitor is charged completely, there is no current flow.
Our final topic will be Kirchhoff's laws, circuit-related laws that deal with current flow and voltage drop. The first of Kirchhoff's two laws states that the voltage around a closed path in a circuit must sum to zero, as can be seen in this fantastic example.
The second law states that the current entering a junction must equal the sum of the currents exiting a related junction.
Although you may encounter circuits with multiple batteries at different points, in this case we will focus on circuits with only one battery. As you can see, the initial current I splits into IR1 and IR2, and then rejoins after the parallel branches come together. Also, the voltage goes from an initial chosen value to a final value of 0 right before the current reaches the negative node of the battery. This is an example of an advanced RC circuit with multiple batteries. Although we will not be going into the specific mechanics of such a circuit, you can use Kirchhoff's laws to find multiple values such as voltage and current at different points in such a circuit.
Thanks for watching. We hope this video improved your knowledge of both DC and RC circuits.